We're going to move now to a topic very different than what we've covered so far. Regression and correlation have to do with prediction, a fundamental goal in many of the social sciences. Given knowledge about one characteristic or of a person or a group, can we predict something else about them? We touched on this in our discussion of chi-square and crosstab tables, but those concern nominal variables, and in any event, the focus was on improving our ability to predict what category somebody was most likely to be in. With regression and correlation, our focus is more precise. The place to start with all this is a discussion of correlation, which begins with the scatter plot. The chart on the right is a scatter plot. The table on the left is the data table showing the data used to create that scatter plot. Each dot on the scatter plot indicates a case. For example, the highlighted point represents the case highlighted in the table. By convention, the independent variable is shown on the x-axis, and the dependent variable is shown on the y-axis. The blue line is called a regression line. It's the only line that can be drawn through this set of points that minimizes the distance between itself and the other points on the graph. As you can see, the line only touches one of these points. You could draw a line that touches 2 or possibly 3 points, but if you added up the distances between that line and all the other points, it would be greater than the distances shown on the line in this plot. As I said, the first step in an analysis that explores relationships between interval ratio variables is to create a scatter plot. Scatter plots can show you a number of things about such relationships that are important to know going forward. Let's take a look at a couple of scatter plots. So this slide shows the relationship between the age at which women marry and the age of their spouse. The points show a positive trend. As the age at marriage of the woman goes up, the age of the men they marry goes up as well. This slide shows the relationship between births and literacy rates. It depicts an inverse or a negative relationship. As a country's literacy rate goes up, the total number of births per family goes down. This scatter plot shows the relationship between the age of a marathon runner and that marathon runner's time. The points don't seem to show any particular pattern. There are some younger runners with very fast times and some with slow times. Even runners in their 50s can report short times. If you drew a regression line through these data, it would roughly be parallel to the horizontal axis, indicating no relationship. In addition to showing the direction of a relationship, a scatter plot can also depict its strength. The points here are packed fairly tightly together, and if we drew a line through them, the distance between that line and all the other points would be relatively small. In addition to showing the direction of a relationship, a scatter plot can also depict its strength. The points here are packed fairly tightly together, and if we drew a straight line through them, the distance between that line and all the points would be relatively small. This slide also shows the correlation coefficient R, or Pearson's R, which is associated with this data. In the social sciences, anything above 0.75 or so is considered a strong relationship. Note, however, that these are just rules of thumb. This strong or not so strong stuff, really just rules of thumb. There's no hard and fast boundary for a strong or any other characterization of a relationship. This slide shows a moderate correlation. Note the value for R. And a weak correlation. Now, note that these three correlation coefficients, the ones we've seen in the last three slides, are all positive. We can have a negative correlation as well. That would indicate an inverse or a negative relationship. As the independent variable shown in the x-axis increases, the dependent variable on the y-axis decreases. Coefficients that approach -1 indicate a strong inverse relationship, and those that approach 0, such as -0.2, indicate a weak relationship. This scatter plot shows a curvilinear relationship. As temperature goes up, the level of ozone in the atmosphere rises, but it rises at an increasing rate. The techniques we're going to learn here only apply to linear relationships. So if you run a plot and it looks like this, it's time to stop and select a different analytical strategy. All right, let's summarize this stuff about scatter plots and Pearson's R. First, values range from -1 to +1. If you've calculated something outside of those boundaries, you made a calculation error. Values close to -1 or 1 indicate a strong relationship. Values close to 0 indicate a weak relationship. Positive values indicate a positive relationship. As x goes up, y also goes up. Negative values indicate an inverse or negative relationship. As x goes up, y goes down. Here's the formula for computing Pearson's R. It's the sum of the z-scores for x and y divided by n minus 1. You can use a summation table similar to the one in the box to compute the values. Hopefully you remember how to compute z-scores. You take each value for x, subtract the mean of all the x's, and divide by the standard deviation for all the x's, and then you do the same for the y values. That gives you the z-scores, which you then multiply which you then multiply together, add up those products, and divide by n minus 1. You can check the lecture notes or your text for more details if you need them about how to do this summation table. The version that I've given you here assumes that you can compute those z-scores on the fly. Okay. This scatter plot shows the vertical drop in feet as the independent variable against the duration of a roller coaster ride. Just glancing at it, it appears to slope upward, indicating a positive relationship. And as the height of the coaster increases, the duration of the ride also increases. So again, a positive relationship. Let's add a regression line to this. As you may recall from high school algebra, a graph drawn like this can be described by an equation that indicates the slope of the line and where it crosses the y-axis. That line is defined by this formula. B is the slope of the line, and A is the intercept, the point at which that line crosses the y-axis. This is also the point where x equals 0. If you know the slope and the intercept, you can easily compute the y value associated with any x value. The slope and intercept for a regression line can be easily calculated using a formula I'll present you in a minute. Just recall right now that the regression line is drawn in such a way that it minimizes distances from each point to that line. For this particular scatter plot, the regression line looks like this. What this means is that for every 1 unit increase in the height of a roller coaster, the duration of the roller coaster ride increases by 0.4 seconds. So suppose we want to predict the length of a roller coaster ride that has a height of 250 feet. For a vertical drop of 250 feet, we simply multiply 250 by 0.4 and add 87 to find the predicted duration of the ride. This formula for this set of data gives us an estimated ride duration of 187 seconds based on a vertical drop of 250 feet. Here's the formula for calculating this B value. To find the value for A, simply multiply the slope you've just calculated by the mean for all the x values, subtract all the y values, and you have it. Okay, so regression and correlation can be quite a bit more complicated than what I've presented here. It's so complicated, can become so complicated, that it would be easy to build an entire course around just regression. Your text discusses the math in more detail and introduces tests designed to assess the statistical significance of R and the regression coefficient B. But beyond that, it's also possible to trick the linear model so that you can include nominal independent variables and even use nominal dependent variables. But those are all subjects for a much more advanced course. Okay, I hope you found this helpful.